So I guess I'll get started. My name's Matt Owers. I'm from Macquarie University in Sydney, Australia. So I'm coming to you some hours in the future compared to the majority of you, I guess. It's 10 p.m. at night here at the moment. So it's well and truly into the night time. But I'll be talking to you about something that I've been interested in for some time, the interaction between the ICM and galaxies in merging clusters. And I just want to start by thanking the organisers for giving me the opportunity to talk to everyone about this topic, because I think it's kind of interesting as well. So I guess I'll start with a little bit of motivation as to why we might be interested in galaxy clusters, and um, this is viewed through the lens of my own interests. So people may have their own interests as to why they might want to study galaxy clusters, but my own interests lie in understanding why galaxies look the way they are and why things correlate with environment. So we've known for a long time, actually, since the 1980s, that the morphology of a galaxy correlates quite strongly with an environment. And this is the well-known morphology density relation from Alan Dressler in 1980, which tells us that in the dense cores of rich clusters of galaxies, we're more likely to find S0 and elliptical type galaxies that are devoid of star formation when compared with the lower density field environments where we see a larger fraction of spiral galaxies rich with star formation. So more recently, surveys like the 2DF GRS, which was conducted here in Australia, the Sloan Digital Sky Survey in America, and the Galaxy and Mass Assembly Survey, also conducted here in Australia, have really nailed down some of these correlations with environment, and in particular have focused as well on what the star-forming properties of galaxies look like as a function of environment. We see fewer star-forming galaxies in the rich cores of clusters, and we also see that the star formation rate of star-forming galaxies decreases as you head towards the centers of groups and clusters of galaxies, all of which indicate that the environment is an important in shaping the properties of galaxies in terms of their morphology and their star formation. And I guess now the big question is trying to understand what drives these correlations. And here again, I think clusters are really important. They're the densest regions that we see in the universe. They host a plethora of different environmental processes that we can investigate within these regions. And this is, I think, shown quite nicely here in this slide that I stole from R.E. Chung, who basically has given a schematic showing what a galaxy goes through in its everyday life as it resides in a galaxy cluster. And this is sort of broken into interactions, gravitational interactions, for example, tidal and compression and truncation interactions with the gravitational potential well of the cluster as a whole that can drive star formation in these galaxies. Harassment, which can also drive star formation, but also pulls gas and stars away from the outer parts of galaxies, changing their morphologies and potentially stopping their star formation. Mergers, probably not so important in the cores of clusters where the velocities are probably too high for things to stick together, but may be important in pre-processing as groups fall into clusters. Some of the things that I've been more interested in and I'll be talking about a bit later on are the interactions with the ICM and galaxies. So one of the more well-known interactions is that of rare pressure stripping, where the wind felt by a galaxy as it rushes through the intracluster medium strips off gas and stops star formation in the galaxy without significantly altering the morphology of the stars and the distribution of stars. And you can see some spectacular trails of gas and star formation that we'll look at a little bit later on in these rare pressure stripping events. There's also other aspects like starvation, which is probably important on long time scales and may well be important in groups and also in the outskirts of clusters in terms of reducing the star formation of galaxies in clusters. So that's basically, some of the processes that a galaxy feels in just a normal, relaxed, everyday sort of cluster. But what about cluster mergers? So why are they important? Well, cluster mergers, the major merger of two clusters is the pinnacle of hierarchical structure formation. So it's one of the most, it is actually the most energetic event in the universe after the Big Bang. So if you've ever read a paper describing the major merger between two clusters, you will have come across the line that, they release 10 to 64 ergs of energy, and most of that goes into driving shocks and compression of the intracluster medium, as well as speeding up the galaxies as they collide. So these clusters collide at somewhere of the order of 3,000 to 4,000 kilometers a second. So there's a lot of interesting stuff that can be learned from these clusters in terms of intracluster medium physics that we can learn from shocks and cold fronts. We can learn a lot about the ICM. We can learn a lot about particle acceleration by observing radio halos and relics that we see in these clusters, cluster mergers. We can also learn a lot about dark matter physics, and everyone, I guess, will be familiar with the bullet cluster and the impact that it's had on understanding dark matter in our universe. You'll also know from Gabriel Pratt's talk yesterday that we need to understand cluster mergers if we want to use clusters as cosmological probes for scaling relations and all that sort of thing. They can really muck up the scaling relations for mass measurements of clusters. So the other thing that's really interesting is that these violent environments probably drive enhanced or accelerated galaxy evolution. And it's been an open question for some time as to exactly what happens in these cluster mergers to galaxies. So the high speed mergers, as I said, drive shocks, compression of the intracluster medium, whether this strips galaxies of gas and leads to quenching of star formation, or whether the enhanced pressure leads to triggering of star formation is sort of an open question that we've been trying to address for, I guess, over 20 years now. And I think the punchline of this talk will be that we aren't quite there yet, but if someone's willing to do the work, we probably can get there in the next 5 or 10 years, I hope. I'm probably not going to do that work though, so maybe one of the younger PhD students might want to address that. So I guess for the rest of the talk, I'm going to go over a few different ways that cluster mergers can impact the unfortunate galaxies that are involved in these cluster mergers. So I'll start with just a few simulation results, so idealized simulations that have been used to try and understand the impact of cluster mergers on the resident galaxies. And then I'll go on to talk about what's been done observationally to try and look at whether these cluster mergers in fact enhance star formation or whether they preferentially quench star formation during the merger process. So the first port of call here is to try and understand or to look at simulations that show how the high-speed merger process can strip potentially star-forming gas from these galaxies. And I think this has been looked at over 20 years ago now by Fujita and other people. But I think that this paper by Domenko, whose main aim actually was to look at the enrichment of the intracluster medium due to ram pressure stripping of satellite galaxies, is probably one of the better showcases of how mergers impact galaxies because of their increased ram pressure. So they looked at three idealized simulations of 3 clusters, 2 of which had pretty benign merger histories. They underwent some minor mergers, so mass ratios of less than 1 to 4 or so throughout the course of their history. And they also looked at one cluster that underwent a major merger of around about a 1 to 3 mass ratio at around about a time of 4 billion years. And so what they looked at was the mass loss rate as a function of time. That's what's plotted down here. And you can see that at 4 billion years timescale, the mass loss rate from ram pressure stripping in the merging cluster, which is shown by the solid line here, increases by an order of magnitude. And again here at around about 7 billion years, when the cluster, the subcluster turns around and comes back for its second pericenter. So I should say this coincides with the first pericenter passage of the cluster merger. So you can see that there's a strong enhancement of the ram pressure due to this high speed, several thousand kilometer a second cluster merger that's going on in this cluster number 2 in their simulations. And they didn't talk about quenching of star formation in this paper, but it's not too much of a stretch to imagine that this enhanced ram pressure stripping that's felt during this cluster merger undoubtedly leads to a more significant and a more accelerated quenching of star formation, just because there's just no gas left in these galaxies in order to form stars anymore. So we might expect that major mergers, given this simulation, drive quenching of star formation rather